नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT जेईई एंड नीट। ये लिक्विड सॉल्यूशन का दूसरा पार्ट है और ये जेईई मेंस रिवीजन का 5वां दिन है। इसमें हमने हेनरी लॉ को डिस्कस किया है और बाइनरी सॉल्यूशन इन विच बोथ कंपोनेंट्स आर वोलेटाइल उसको डिस्कस किया है, और साथ में बहुत सारे फैक्ट्स जो जेईई मेंस के हिसाब से बहुत इंपॉर्टेंट है, एग्जांपल्स ऑफ नेगेटिव डेविएशन, पॉजिटिव डेविएशन, आइडियल सॉल्यूशंस। वी हैव डिस्कस ऑल दोस पॉइंट्स। So let us start liquid solution part 2. So till now we have covered the 4 colligative properties. Now we are discussing when both components are volatile. When both components are volatile, we don't want to discuss colligative properties. Colligative properties are only valid when the solute is non-volatile. So binary solution having both component volatile. So let us start one by one. First we are discussing about ideal binary solution. So we have two components. So the force of interaction between A and A component, same type of particles, is known as cohesive forces. The force of attraction between B and B is cohesive forces. The force of attraction between A and B is known as adhesive forces. So when we are making an ideal solution, the force of attraction between AA, BB is equal to the force of attraction between AB. So on mixing, there is no change in interactive forces. So because of that, on mixing, the volume will not change. The volume of the solution is equal to the volume of pure component A plus volume of pure component B, or we can say that delta V mixing is equal to 0. Volume is not changing because intermolecular forces are not changing. Examples of ideal solution: when same type of components are going to mix, like when we are mixing benzene and toluene, or when we are mixing benzene and naphthalene, they are hydrocarbons. When hexane and heptane are mixed, or methanol and ethanol are mixed, these will form ideal solution. So one question is, which of the following is ideal solution? So there are same type of compounds, when mixed they will form ideal solution. Now D option is important for us because we know that what is definition of solution. Definition of solution means it is a homogeneous mixture of two or more than two component in a single phase. When we mix two ideal gas, so two ideal gas on mixing will form an ideal solution because there is no interactive forces. So we can say that there is no change in volume if we are mixing at constant pressure and temperature, right? So here we are discussing that not no change in volume, that is not right. Okay, so mixing of two ideal gases at constant temperature and pressure. So here a container is there where number of moles of gas A is Na, and the gas is at pressure P, temperature T, and it is present in a container of volume Va. There is another where the number of moles is Nb, pressure is P, temperature is T, and volume is Vb. Since the temperature is constant, on mixing these two gases, there is no enthalpy change, because we know that enthalpy of an ideal gas only depends on temperature. Temperature is not changing. Delta H is 0, delta H will be 0, so delta H mixing will be 0. Now we want to know that what is entropy change on mixing. So what is happening when we are removing this stopcock? This gas A initially was in the left hand side container. Now it is present in left as well as right hand side. So whole volume is available for this gas A. Temperature is not changing. So an ideal gas participating in any process, if we write what is the entropy change, that is N Cv ln T2 upon T1 plus Nr ln V2 upon V1. So here T1 and T2 are equal, so that will be 0. First term is 0, so we are writing NAR ln V final is equal to volume of gas A plus volume of gas Va plus Vb, volume of both the containers, upon initial volume is Va. So we know that what is the initial volume of container Va, PV is equal to nRT. From there Va is equal to NART by P. So NART by P, Vb is equal to NBRT by P upon Va NART by P. So RT by P will cancel out, Na plus Nb upon Na, which is 1 upon mole fraction. So if I simplify, if I multiply and divide by N total, Na upon Na plus Nb, Na plus Nb is N total. So Na upon Na plus Nb is mole fraction of A. So I am taking N total in numerator and denominator. And then I can simplify this as minus n total into R XA ln XA. XA is less than 1. So ln XA is negative, negative and negative is positive. So entropy is going to increase for gas A. Same way we can say for gas B, entropy is going to increase and that is equal to minus times of n total R XB ln XB. So total entropy change on mixing is positive. That is equal to minus n total R XA ln XA plus XB ln XB. So entropy change of mixing is positive. And this process is taking place at constant temperature. So delta G mixing is equal to delta H mixing minus T delta S mixing. Delta H mixing is equal to 0. So from there we can say that delta G mixing is equal to minus T delta S mixing, which is negative. So we can say that it is a mixing is a spontaneous process and it is entropy driven process. It is entropy driven process. And when we are mixing, there is no change in interactive forces, means there is no exchange of heat energy between system and surrounding. So entropy of surrounding is not going to change because there is no exchange of heat energy between system and surrounding. So entropy of surrounding is not going to change. So when we are talking about ideal gas, first we know what are the examples, then we should know delta V mixing is 0, delta H mixing is 0, delta S mixing is positive, delta G mixing is negative. So here we are discussing about two volatile component A and B. So this volatile component A is present in this container at temperature T. It is pure. So vapor pressure of this is equal to P naught A. In another container B is present at same temperature. P naught B is the vapor pressure. When we mix these two to form an ideal solution, then vapor pressure of the solution is P total, which is equal to vapor pressure of A plus vapor pressure of B. Using Raoult's law, we can write that vapor pressure of A is equal to P naught A XA and vapor pressure of B is equal to P naught B XB. So P total vapor pressure of the solution is P naught A XA plus P naught B XB. And you should also have an habit of writing. If you have to write in terms of XA, if I have to write in terms of XA, then P naught B will come plus, since XA is there, P naught A minus P naught B. If I have to write the relation in terms of XB, then I should write P total is equal to, since as XB is there, P naught A plus P naught B minus P naught A, right? So you should practice these formulas. While applying it, it should not take much time, right? So practice it. So what we are discussing here, that this XA and XB is mole composition in liquid state, right? Composition in mole fraction in liquid state, and YA and YB in composition in vapor state. So in vapor state, this is Dalton's law, this is Raoult's law, and this is Dalton's law. So in Dalton's law, we say that vapor pressure of component A is equal to mole fraction of that component in vapor state into P total, or mole fraction of that component in vapor state is equal to partial pressure of that component upon P total. If I simplify, we can write P naught A XA upon P total, right? And there are many questions based on that, but we are not discussing here. So this is the graph of vapor pressure of the solution versus composition. So here mole fraction of the A component, here we assume that A component is more volatile than B component. So XA is equal to 0 and here XA is equal to 1, means pure A is there. So vapor pressure of A is P naught A. Here XA is 0 means XB is equal to 1. So here pure B is there. Vapor pressure of that is P naught B. So during the formation of the solution, this is the variation of vapor pressure of A with composition. PA is equal to P naught A XA. And we can say here that as we are increasing the mole fraction of A, the vapor pressure of A in the solution is increasing. And the total, this is for total vapor pressure. So if we increase the mole fraction of more volatile component in liquid phase, then the vapor pressure of the solution is going to increase. From this graph, we can conclude that, right? Same way, we can find out that this is for less volatile component. So as we are moving on the left hand side, we are increasing the mole fraction of more volatile component. As we are moving in left hand side, we are increasing the mole fraction of less volatile component. If the mole fraction of less volatile component is increasing, the vapor pressure of the solution is decreasing. So there are many conceptual things which we can discuss from this graph. Now, negative deviation from ideal behavior. Negative deviation means the force of attraction between A and B is greater than the force of attraction between AA or BB, or adhesive forces is greater than cohesive forces. So on mixing, a force of attraction will be more, the particles will come nearer to each other. If they will come nearer to each other, then the volume of the system is going to decrease. So that's why we are saying that delta V mixing will be negative. When the interactive forces will be more, we can say that on formation of bond, energy is released. So in this process will be exothermic. Delta H mixing will be negative. And since on mixing, the solution is forming, it is a spontaneous process. So delta G mixing will be negative. And we are using this delta G mixing is equal to delta H mixing minus T delta S mixing. This delta G mixing is negative, delta H mixing is negative. What about delta S mixing? For most of the solution, not for all solution, but for most, if they are asking in mains, definitely this will be the answer. For most of the solution, entropy change on mixing in case of negative deviation is positive. There are few exceptions we are not going to discuss here, but if they are asking, you can say that delta S mixing in case of negative deviation is also positive. So again, this is the graph, and now you can compare here that with respect to the ideal solution, the vapor pressure of A in the solution will be less. Means we can say that vapor pressure of A in the solution, because Raoult's law is not valid, so I cannot say that it is P naught A XA. But we can say whatever the vapor pressure of A in the solution, it is less than P naught A XA. What is the vapor pressure of B in the solution? It is less than P naught B XB. Whatever the total vapor pressure of the solution, it is less than P naught A XA plus P naught B XB. Examples of negative deviation. This is very important in JEE Advanced as well as JEE Mains. So please revise these, right? It is based on memory, but it will give you marks in the exam. So very logical. Negative deviation याद करने का तरीका बहुत logical है. अगर हम किसी एसिड और बेस को मिक्स करेंगे इन आयनिक इक्विलिब्रियम, वी स्टडी दैट एसिड बेस रिएक्शंस आर एक्सोथर्मिक रिएक्शंस. So delta H will be negative. So when we are mixing two liquids and those liquids, one is acid, other is base, then delta H mixing will be negative. It is negative deviation. So the first is mixing of acid and base. You know that phenol is organic acid and aniline is organic base. Pyridine is base, formic acid is organic acid. They are in liquid state at room temperature. Pyridine and acetic acid, pyridine and propanoic acid. So these examples are based on mixing of acid and base. Then the second example, when we add strong acid in water, like in lab, you know that H2SO4 is a liquid. When this H2SO4 is added to water, it is an exothermic process, because this H2SO4 will ionize, and due to hydration of those ions, more energy will release. So it is an exothermic process. So H2SO4 is a liquid when it is mixed with water. HNO3 is a liquid when it is mixed with water. HCl is a liquid when it is mixed with water. Then it is an example of negative deviation. And the third example is mixing of organic compound containing nitrogen or oxygen or both with chloroform. When nitrogen, oxygen, or compound containing nitrogen and oxygen both is there, they can form hydrogen bond with chloroform, and because of that there is negative deviation, like acetone and chloroform. Like this is amide, acetamide and chloroform. So any or organic compound containing nitrogen or oxygen, when it is mixed with chloroform, due to hydrogen bonding, there is negative deviation. And this is a typical example where there is a hydrogen bonding between this hydrogen of chloroform and pi electron cloud of benzene. So due to hydrogen bonding, it will give negative deviation. So these are the examples, and the examples of negative deviation is more logical to remember, and these questions are very common in exam. It is important for JEE mains as well as advanced. So please revise it. Now taking positive deviation from ideal behavior. So we can say that in positive deviation, the force of interaction between A and B is less than the force of interaction between AA and BB. So what will happen that when there is less interaction, then the particles will be away. So volume will increase. So delta V mixing will be positive. In terms of bond energy, we can say initially the bonds are more stronger. The bond between AA and BB is more stronger than AB. So when the bond will form, energy will release. But if reverse is happening, means energy will absorb. So this is an endothermic process, and this energy is taken from the surroundings. So surrounding is giving heat energy. So we can say that the entropy of surrounding will decrease in this process. Since the solution is forming, so we can say that it is an spontaneous process, then delta G mixing will be negative. And since the surrounding is losing heat energy and system is gaining heat energy, entropy of the system is going to increase. So delta S mixing will be positive. So always remember, either it is ideal solution or it is non-ideal solution, either it is positive deviation or in negative deviation, entropy change on mixing of the system is going to increase. Now there are 9 examples, and these 4 examples are given in NCERT, and all these examples are asked in exam from time to time. So if you are able to remember these 9, then it is fine, but these 4 are compulsory. In which one, when alcohol and water is mixed, it is positive deviation. Alcohol and water, acetone and carbon disulfide, ethanol and acetone, and normal heptane and ethanol. And don't put some logic, there is no logic, because theoretically there are many factors. Which factor will dominate, we don't know. So it's better to put your energy in mugging these examples for positive deviation. Don't make some logic. There is no logic, your logic will fail. So after a long time experience, I am saying that mug up before exam. And these 4 are very important. They are given in NCERT, and many times they have asked in exam. And same way we can say that if we compare here now in positive deviation, I can say that for component A, the vapor pressure of A in the solution is greater than the vapor pressure when it is behaving idly. When it is behaving idly, it is P0 AXA. So in this positive deviation, we can say that vapor pressure of B is greater than P0 BXB. Or we can say that vapor pressure of the total solution here, vapor pressure of the total solution is greater than the vapor pressure with respect to when the solution is behaving idly, that is P0 AXA plus P0 BXB. Sometimes what they will do, they will give the composition, they will give the vapor pressure of pure component, and they will give the total vapor pressure, and they will ask that this solution is negative deviation, positive deviation, or ideal. So by using this formula, you will find out what is the vapor pressure total when the solution was ideal. P0 AXA plus P0 BXB is valid for ideal, and then you can compare. If this P total, experimental or given value, is greater, then it is positive, is less, then it is negative, and if they are equal, it means that the solution is behaving ideally. Henry law. So Henry law, it is regarding dissolution of gas in liquid, and when we are discussing about dissolution of gas in liquid, we are discussing about intermolecular force of attraction. When gas is dissolved, means there is a force of attraction between gas particle and water. Like we have already discussed that solubility of noble gases increases down the group, because as we go down the group, water is polar in nature, but helium, neon, argon, krypton, the London dispersion forces is going as the molar mass is increasing, and because of that solubility is increasing. So when we are discussing about Henry law, we are discussing the same thing. If I have to give a logic between nitrogen and oxygen, both are non-polar gases. The molar mass of nitrogen is less, the molar mass of oxygen is more. So I can say that oxygen is more soluble. If there is no extra bonding like hydrogen bonding or something, for a non-polar gas, we can apply that concept that solubility is directly proportional to molar mass, right? So it is always exothermic process. Why it is exothermic? Because there is bond formation between gas particle and liquid particle. That's why gas is inside the liquid. It is in the space inside the liquid. So it is an exothermic process, and we know that if the process is exothermic, what is the favorable condition for dissolution of gas? So favorable condition is low temperature, since it is an exothermic. Low temperature is required. And high pressure. Why high pressure? Because if I want to dissolve the gas in this liquid, if pressure will be more, then the probability of colliding this gas particle with this liquid will be more. Then only they will dissolve. So more pressure means more interaction between gas and liquid, and more chances of dissolution will be there. So high pressure and low temperature condition is the condition, favorable condition for solubility of gas in a liquid. Now, why we are studying Henry law? The first thing is water life. Most of the food in this world is from sea, not from agriculture and all. Sea से ही ज़्यादा खाना आता है पूरे world में. So the sea food is dependent on sea life, and sea life, there is no life in hot water. जैसे क्या होता है कि during winter कई जगह पे on the sea there is a layer of ice, right? But below that water is there, and in that water there is dissolved oxygen, and those dissolved oxygen is taken by the animals. So aquatic life के लिए water के अंदर oxygen का होना जरूरी है, and in hot water there is no oxygen, there is no life. So one thing which is important, that dissolution of gas in a liquid is dissolution of oxygen gas in water. And the second thing is scuba diving. When we go deep inside the sea, this point is very important for us. So we have an habit, our body is working under normal atmospheric conditions. So when we go inside the sea, the external pressure is going to increase. Due to atmospheric pressure, that pressure is there. Due to the height of the liquid, there is an extra pressure. So inside our body there is blood, and in that blood, when we inhale oxygen and nitrogen is there, and we need oxygen, right? So dissolution of oxygen is there. So if we increase the pressure, what will happen, that the dissolution of gas will increase. So we have to maintain that a proper amount of oxygen will dissolve, and not extra unwanted thing will dissolve, right? So what we do, that in scuba diving, to avoid bends is what, that in our body when we are inside the sea, the dissolution of gases will be more, right? So when we come up, those dissolved gases inside our blood will try to come out, because high pressure was there inside, so that they are dissolved. But when we come up, pressure is decreasing, so that gases will coming out. So when they will come out, they will there will be a pain, right? So there is bent in our body, right? So that is related to avoid bends, the tanks by scuba divers are filled with air diluted with helium. This is given in NCERT, so be careful about this knowledge, right? Helium, we are diluting with helium, because the dissolution of helium in water is very less, and our blood is 90% water only. So when we are discussing about Henry law, what we say, that if we increase pressure, the solubility of the gas is going to increase. So solubility of gas is directly proportional to pressure of gas, and Kh is the Henry constant. The value of Henry constant depends on solvent, it depends on the gas, right? So this is a constant known as Henry constant. So when I am writing the Henry law in this form, the unit of Henry constant is equal to unit of pressure. If nothing is mentioned about the unit, then we'll take what is given in NCERT, because when we are saying pressure of the gas is directly proportional to solubility of the gas, this proportionality constant can be on the left hand side or right hand side. So in many books they can change the position, but if nothing is mentioned, we have to follow NCERT. For mains especially, it will follow what is given in NCERT only. So Henry constant unit is that of pressure, means this formula is valid. There are many ways to represent solubility. One of the way which we are following in NCERT is mole fraction. So in our course, they have given that pressure of the gas is equal to Henry constant into mole fraction of the gas. So when we are solving a question of Henry law, first we have to be careful about the unit of Henry constant. Be careful about the unit of Henry constant. If nothing is mentioned, then we'll follow NCERT, and according to that, the unit of Henry constant is that of pressure. So if it is correct that unit of Henry constant is that of pressure, then Henry constant and solubility are inversely proportional. So higher the value of Henry constant, means less will be the solubility of the gas. So solubility is inversely proportional to Henry constant. On increasing temperature, we know that if we increase the temperature, solubility will decrease. If solubility will decrease, it means that Henry constant will increase. So they can ask, for the same gas, if we increase the temperature, what will happen to Henry constant? Henry constant will increase on increasing temperature. And last point, we can say that higher the value of Henry constant means low solubility. If the Henry constant is low, means high solubility. So in your NCERT, there is a table, and I am saying that since the table is given in NCERT, that's why it is important to go through the table. They have given the solubility of many gases in water. So if you go through that, you will find that formaldehyde is more soluble in water than methane gas. Methane gas is more soluble in water than vinyl chloride, and CO vinyl chloride is more soluble than CO2 and CO2 is more soluble than argon. These things are given in NCERT. If you are able to remember it, it is fine. Otherwise, you can forget also, right? Since it is given in NCERT, and if we don't read it, we not able to know that which gas is more soluble. So formaldehyde is more soluble among all these gases. And this is the best question which is asked in JEE 2009 about Henry law. So it's a simple question. Let us solve this question. The Henry law constant for the solubility of nitrogen gas in water at 298 Kelvin is 1 into 10 to the power 5 atm. The mole fraction of nitrogen in air. So they have given that mole fraction of nitrogen in air is equal to 0.8. And they are talking about a total pressure of 5 atm. So from here we can calculate what is the partial pressure of nitrogen gas, that is 5 into mole fraction, that is 0.8. So that is equal to 4 atm. So nitrogen gas is at 4 atm pressure. And now they are asking that the Henry constant for nitrogen gas is equal to 10 to the power 5. Henry constant is 10 to the power 5 atm. So if we apply Henry law, that pressure of nitrogen gas is equal to Henry constant into mole fraction of nitrogen gas. From here we can calculate that mole fraction of nitrogen gas is equal to 4 into 10 to the power minus 5. This is a very small value, means very dilute solution. So I can write that is equal to number of moles of nitrogen gas upon total number of moles of nitrogen gas plus number of moles of water. The number of moles of water given is 10. So here, since this value is very small, I can neglect this number of moles of nitrogen. From there we can write that number of moles of nitrogen is equal to 4 into 10 to the power minus 4. So 4 into 10 to the power minus 4 moles of nitrogen is dissolved in 10 moles of water. So I think first option is coming, right? So Henry law is very important. Now these are information given in liquid solution chapter and they are asked in JEE mains, right? So this is about alloy. So German silver mains में पूछा गया था, right? तो German silver में there is no silver at all. It is a alloy of copper, zinc and nickel. Please revise before exam. Bronze and brass में याद करने का तरीका क्या है? जहां Z है वहां जिंक नहीं है. So bronze में जिंक नहीं है, copper and tin. और brass में zinc है. So copper alloys, these are copper alloy. Copper and tin is bronze and copper and zinc is brass. This is also given in liquid solution NCERT और ये पूछे गए questions JEE mains में. 1 ppm of fluoride ion in water prevent tooth decay. Toothpaste में fluoride होता है. 1.5 ppm of F minus cause the tooth to become mottled. Mottled means जो tooth होते हैं वो decay कर जाते हैं, right? So this is a disease. So large amount like 1.5 ppm is not it is harmful, right? And sodium fluoride हम use करते हैं as a poison. अगर हमें rat को kill करना है, in killing the rat we are using this sodium fluoride. So this information is also giving in NCERT. Please go through it और exam से पहले इसको पढ़ के जाना, ठीक है? Amalgam, you know that amalgam we are dissolving some metals in mercury, right? Sodium dissolved in mercury. So solid in liquid, it is a type of solution, solid in liquid. We are dissolving solid, we are dissolving metals. Most of the metals are solid. We are dissolving in liquid, that is mercury. Then simple distillation, fractional distillation. We know that we use the concept of simple distillation when the difference between the boiling point of the two component, difference between boiling point of two component is greater than 25 degrees Celsius. And fractional distillation, we are using fractional distillation when the difference between the boiling point of two component is less than 25 degrees Celsius. Petrochemical industry में we are using fractional distillation. Steam distillation, steam में steam water होना जरूरी है, right? Steam word is used for water. So when we have to separate aniline C6H5NH2 and water, if we have to separate this aniline, is there something with impurity के साथ में aniline है, and we want to remove this aniline. So what we'll do that, aniline has more boiling point than water. The boiling point of aniline is 184 degrees Celsius. So what we'll do that, this impurity and aniline was together. So we are putting this water, and these are immiscible. They are not very miscible. So what we are saying that when we put water, water is more volatile. So we can explain here that their solubility, aniline and water are less, they are immiscible, right? So what we are doing here, that steam distillation concept is that when we put together, the vapor pressure of pure water is P naught H2O, and the vapor pressure of aniline will be P naught, because they are immiscible, so they are pure. So if they are pure, the vapor pressure will be same. So now when we are putting together, the vapor pressure of the whole system is going to increase, and when the vapor pressure of this system is equal to external pressure, this whole system will boil at low temperature. They will go in vapor state. When they will go in vapor state, the substance which has more boiling point can exist, can the substance which has less boiling point, like water has less boiling point. So when we decrease the temperature, right, when we decrease the temperature, it has less boiling point, so it will condense and they will separate out. So water and this aniline can be separated by steam distillation. So steam distillation is used when the boiling point of the substance is very high. So either a lot amount of fuel is required to vaporize it, or uh, it can decompose before boiling, right? So in that case, what we do, that we mix this substance with more volatile component, and this should be immiscible. When they are immiscible, the total vapor pressure is greater than external a particular component. So if we increase the vapor pressure of a liquid, its boiling point is going to decrease. So the whole liquid can go into vapor state, and then we can condense them and separate them. And they are immiscible, so they can be separated. So this is already asked in JEE Mains. Steam distillation NCERT में दे रखा है, water and aniline, steam distillation, they are separated, water and aniline. Then soap industry, this is also asked in JEE Mains. Soap industry, it is also given in NCERT. Glycerol, because glycerol, because of OH group, there is hydrogen bonding, so its boiling point is very high. So glycerol and spent lye, glycerol and spent lye are separated by distillation under reduced pressure. So again here the concept is, if you decrease the external pressure, reduced pressure means external pressure is decreased. If you decrease the external pressure, the boiling point will become less. If the boiling point will become less, so the substances like glycerol and spent lye can be separated. So reduced pressure, glycerol and spent lye. Aniline and chloroform, the boiling point of chloroform is 61 degrees Celsius, and the boiling point of aniline is 184 degrees Celsius. Difference is very high. We can separate them by simple distillation. So these examples are given in NCERT. Please go through them. Aniline and chloroform by simple distillation, glycerol and spent lye by reduced pressure. Steam distillation, we can separate water and aniline by steam distillation. So I want to say you that this liquid solution chapter is very important with respect to JEE Mains. In each paper, there is at least one question. Any shift, evening, morning, right? One question will be there, and many questions based on memory. So before exam, please go through the things which I have discussed. और अगर आप लोगों को ये वीडियो पसंद आया तो प्लीज लाइक इट. इट गिव्स अ लॉट ऑफ करेज टू डू मोर बेटर in coming videos. Your like will matter a lot for me. Thank you.